Hello there. Welcome back to the Lattice Podcast. This is episode 115. Today, I finally got a chance to sit down with someone I've wanted on the show for a long time. Professor Paul Dalton, the inventor of Melt Electrowriting. Paul is a rare triple threat, a scientist, educator, and futurist. And honestly, going into this conversation, I was a little intimidated. I am not a scientist, and I knew just enough about MEW to be dangerous. But Paul is one of those people who can make complex ideas feel accessible without dumbing them down. By the end of our conversation, I walked away with a real appreciation for why MEW isn't just a technology. It's a movement. I hope you enjoyed this one as much as I did.
Please listen to the disclaimer at the end of this podcast.
Hello. Welcome, Professor Paul Dalton. Really, I highly anticipate this episode for months or maybe even years now. This is a really valuable opportunity for us to get to know you and your work deeply. You are truly a triple threat. You're an inventor, futurist, educator. I would say I'm definitely a futurist myself, and maybe played a role of educator, but not an inventor. So I can't find anyone else, maybe few people that I know who have all three. So we know that you're an inventor of Melt Electrowriting, but not many people know about the origin story, how you grew up in the scientific world back in Perth, Australia, which I didn't even know where that was. So if you can walk us there, it could be interesting to learn about your work and where you are today as well.
Sure. Thanks, Jenny. And it's great to be on here as well. Just have to say that I became a futurist because I had to teach 3D printing for the past over a decade. And so that just became naturally a part of the course and actually analyzing future trends and where things go. But originally, I grew up in a rural part of Western Australia, so outside of Perth. And I'm not sure if you fully appreciate the 1980s, but being a teenager in that time was a lot of boredom. So, being on a farm, there was not a lot happening. And so I got into books a lot. I started wondering about like how this incredible world works and functions. And, I just became a science junkie, I suppose, probably in the by age 16, 17, I kind of wanted to do everything from maths, chem, physics, biology, and that. And so when I went to university, I tried to do something that encompasses everything. I didn't want to drop any of those. And I ended up doing materials engineering. And that seemed to combine all of those different aspects. But it was really I had such a lucky break in applying for what was probably one of the few biomedical jobs in Perth at that time, where I worked in an ophthalmic research institute and we worked on artificial cornea. When I joined, there was only about 3 people in the lab, but we did get money to translate this into a clinical product. And so by the time I finished and I did my PhD after that, during that time as well, it was about 7 years in total. We had about 15 people in the team and we'd been implanting corneas in about 10 people. And it was my job to be in the clean room making these artificial corneas. So it was just like this incredible experience to kind of join when there's hardly anyone in the team, see it grow, and then see that incredible lift that everyone has to do to make something a clinical product that's then implanted into people. And so that really formulated a lot of my research philosophies. Like for me, I want to try and develop new products and new materials that can translate through to the clinic relatively simply, not after a lot of money and a lot of time, which usually seems to be the case. And so my education in my PhD was on the artificial cornea and also the vitreous of the eye. And making these corneas for implantation required a lot of documentation, a lot of dry and boring stuff, but it really did kind of make me understand a little bit of what was needed to do that translation from from a research lab idea into something that's put into people. And then also meeting the people, and you can see how this product changed their lives. These are people that were blind. Suddenly they could see. And, I remember one person was able to see, found a partner, disappeared into the outback of Australia. And the
Wow.
ophthalmologist was saying, no, don't go. I need to follow up on that. And that person would say, don't worry, I'll be right. Off I go. So, there's that human nature as well that comes into what we're doing in biomedical engineering that unfortunately a lot of biomedical researchers don't have that opportunity to actually see, like, and everyone has an important role. Doesn't matter if you're like 10 years before a product is actually put into a person, the stuff that you're doing in the lab is really important. So just early on, I just saw the impact that biomedical materials have on people. And I just treasure that opportunity so much and feel very privileged to be part of it. But I also want to say to all those researchers out there that aren't working near the clinic, well, what you're doing is so important, right, for this translation process. And so, I even though I haven't done a lot of clinical translation since, I've been doing the basic research, knowing that what we're doing is important. So, yeah, it was cool.
I think I saw a figure somewhere. 90% of the scientific research never get into commercial space. I mean, that's just somewhat expected, but it doesn't mean that intellectual pursuit of knowledge is not worthwhile. You just don't know when it's going to realize the benefit. And also, it's funny that I heard you said you had a boring childhood and boring subject. And I would say, like, maybe you need a boring childhood to be creative down the line to really explore this vast space of possibilities.
Yeah, well, I was referring a bit more to like the 1980s. Like, there's no internet, there's no computers, right? If you want to call someone, it's a landline, and you're dialing with a rotary motor. So that kind of there isn't that kind of instant information there. And, boredom is the furnace where creativity can be,
Yeah, Newton
nourished.
Newton got the first principle of physics while in a pandemic. He was falling asleep, probably because of boredom. But I think that's the gist. Is like he was really bored and he was thinking about something and something hit him, and the creativity, inspiration happened. So, anyways, just thought it was funny that you talk about boring
It
quite a
is,
few
it's
times.
super important. And I still try and get bored as well, deliberately, actually, by going on like long hikes and
Yeah, is it called the
stuff like
leisure
that.
time? That's called the
Yeah,
leisure
the leisure
time.
time, just
Yeah.
and then, as scientists, inevitably you start thinking about your work. And so vacation isn't necessarily vacation from your thoughts of science, but it does keep you off the screen so that then you're able to just dream a little bit and think about and reflect, and maybe come back to the lab with some new ideas.
And I know we did a written interview with you a couple years back, and you said you're a huge fan of expedition books. And I think that reflected in your journey, in the science journey as well, because you were in multiple countries doing many research, focusing in adjacent areas, cross discipline, in fact. What did this? You were in what, 6 different countries for years, each different, including China, which I'm happy to see that you were in Shanghai for a while.
Yeah, I've lost track exact. I mean, it's must say 8, yeah, and maybe 8 countries as well.
8 countries.
But to be quite honest, I spent first 27 years of my life in Perth, Australia, in that one kind of environment, sand beaches. Yep, I got that right. A large part of my life, but it was there. But having that opportunity to get a PhD allows you to then get a visa anywhere. And watching all my friends in their 20s travel to Europe and have their big vacations while I was in the lab. Now, when I finished, it was like payback time. And so that was actually 27 years ago that I left Australia, and I've just been kind of traveling ever since. And I think this is one of the things, as a PhD does get you visa opportunities in almost every country in the world.
Borderless,
Um,
no
yeah,
border.
absolutely.
Yeah.
Absolutely. Yeah.
And so when you were deciding allocating relocate to these different countries. It's not a small deal as you get older, obviously. Is there a storyline of how you moved from Perth to what is the next
It was
stop?
Toronto. Yeah.
Toronto, Canada, and then
Oh,
to Europe, right?
yeah. The move to Toronto was, I having worked in ophthalmic biomaterials, I was quite interested in working in the spinal cord and trying to um, help them. And also in the mid-90s, this is when Christopher Reeve, who was the original Superman, had a horse riding accident. And
Yeah,
so,
that was very impactful
yeah,
to a
and
lot of
as
people,
a
actually. I was a huge fan of him.
yeah, and I love sci-fi movies, and yeah, if this could happen to Superman, it can happen to anyone.
Yeah.
Um, just that kind of empathy driven. Oh, okay, let's see if we can help someone there. Also not realizing really how much work has been put into trying to cure spinal cord injury.
Yes.
No, I was probably a bit clueless about that. But I ended up working in the lab of Molly Shoycat.
Hmm.
Not sure if you know of her, but she's a tremendous researcher, and I was working with clinicians and working in animal-based research in that time. So that was a clear motivation. But as most PhD students, I was broke at the end of everything. I sold my car to buy a one-way ticket to Toronto. My partner went with me. She later became my wife and partner for life. But that was a clear, deliberate transition from one topic to another. And then after a few years in Toronto and really enjoying the culture, it was a little bit about, well, do we go back home to Australia and set things up or keep going? And so then Europe's the natural progression. From that point, it was a bit of randomness, like where I ended up. I was a trailing spouse. My partner has the real job, I say, and she was working in a company. So I had a lot of forced movements. Like we're going to, for example, Southampton. And if you have a look at Southampton, it's like, well, there's not really much polymer chemistry there. There's not a lot of tissue engineering. What can I do? And so that forced me to then work in neuroimmunology and work in a neuroimmunology lab. So it's like forced transitions into a different field by moving. And then that just creates the interdisciplinariness of your career.
And of all these adventures, then you invented Melt Electrowriting.
Yeah, yeah. It was an evolution from melt electrospinning because when I moved to Europe, I was actually had the it was 2002, so I could work on this new technology at the time called electrospinning. Okay, and that was in the early years of electrospinning, and my challenge was actually to electrospin directly onto cells, meaning that I couldn't use organic solvents and I had to use aqueous based solutions. And there was a whole plan for my postdoc there. And like within a few months, it was very clear this is failing dismally. And I'm not sure there is any, and even today, no one can electrospin from aqueous solutions onto cells. And that's where the melt came in, right? Yeah.
When we started 3D Hills maybe 10 years ago, I got into a random online quarrel with another professor about electrospinning. I had no idea what electrospinning was. So I think it would be beneficial if you can explain in common people's language of what electrospinning is. I may actually find some graphics to supplement this podcast. Hopefully, I can find some good videos for it so that people can understand. But if you can summarize what this technology is and then how is this important for your subsequent invention, that would be wonderful.
Sure. So electrospinning is when you apply a high voltage to a polymer solution. And I have to warn you, weird things happen when you apply voltages to liquids. And electrospinning is one case. So it starts generating lots and lots of fibers, a little bit like fairy floss, right? If you think about that kind of non-woven material, but it's more compacted. And so these fibers are really small. And the idea of using electrospinning in medical research was that they were similar in size to collagen and
Hmm.
cells grew on them and they love them. They're a very good membrane to work with, but they were kind of being investigated as a scaffold. So
Hmm. So they're
they have
random.
a
It came
roller.
out as
They're
like
random. Yeah,
very random.
you can't put a
You
fiber
cannot
within
predict much.
centimeters of where you want it to go, right? It's just
Yeah.
blasting, spraying onto a collector. And this was the time when I started working with melts because the aqueous polymer solution electrospinning wasn't working. So I started working with melts, and
I see.
they're more viscous. If you think about a plastic that's molten, it has much higher viscosity than, say, honey. And the result when you apply a voltage was actually this much longer elongated column of liquid, meaning that you could start putting fibers approximately where you want. It wasn't very good when it was electrospinning, but actually you could now focus in where the fibers went in a random way rather than a big broad collection. So
Hmm.
hopefully that helps.
Yeah,
Um,
I think that does help. How is this part of 3D printing, and how is this different from extrusion 3D printing? Because you
hmm,
said that we spend a lot of resources in extrusion-based 3D printing, but it's not generating the outcome that we're hoping for. How can MEW or
hmm.
melt electrowriting be different?
Well, the simplest difference is, say, with a FDM 3D printing, so
Yeah.
extrusion FDM, you're
Mhm.
pushing something through a nozzle.
Right.
What we're doing with MEW is we're pulling something from the
Yeah.
nozzle
Yeah.
and we're pulling it onto a flat collector.
Hmm.
So if you're thinking of something being pulled, you might think like on a mandrel, but in this instance, it's a flat collector and it's being pulled by an electric field that's there. And there is a strange phenomena where a column of liquid doesn't break up when a high voltage is applied to it. It's
Yeah.
strange. So we
Interesting.
get the
Yeah.
small fibers by printing at extraordinarily low flow rates. So we pull the thread from the nozzle and we do it at about 5 or 10 microliters an hour. All right. And that's an incredibly low flow rate. That's like 1/10 of a teardrop per hour of
Hmm.
printing rates. And as
Yeah.
a result, you get really small fibers.
Yeah. Do you remember the moment that you felt like this is a eureka moment?
Yeah. I mean, it was one of those things where you're kind of looking down the microscope and you kind of look up and you go, okay. And then you look down again. And yeah, there was a certain breathlessness with what was produced that it was like, oh, okay. I haven't seen this, and this is big, right? Because you know when you're in the at the bench a lot, especially when you're an experienced postdoc, you see a lot of things. You know, I see lots of different techniques and principles, and then this was something I just never seen before, and it happened at just such a phenomenal rate that I it was breathless, and yeah, that was a point where uh, I I went, okay, I'm going to have to dedicate a lot more of my time to this.
And
Um,
before this, did you like go through a lot of different iterations to tinker this process? How many times, I mean, did you fail and stuff like that?
Gosh, look, I think, I mean, yeah, I mean, it would be hundreds of times, right, of different variations. And, you know, looking back now, it made sense because we're working with probably a 10 variable system. So, like, how do you find a sweet spot when there's like 10 different variables that can affect it all? And so you're iterating and you're trying things out. You know, you're getting closer. It's a bit like when you go to an optometrist. They say, you know, is this one better or this one? And so, you know, you're constantly working and finding out that, oh, this is trending in a better way. And then combining with something else, it makes it better. And it takes a long time simply because you're not sure exactly what to do. As soon as you've done it, it's very easy to then instruct someone else to do it immediately. And
Yeah.
I think that's one of the things about not knowing specifically what to do and how it's so easy afterwards. Oh, if I just did this, then all these things would change and
You
it
know,
would
I
be good.
bet it's more than a couple hundred times. I bet it's more than that. You know, the problem with scientific community sometimes we tend to publish success stories. You know, something worked, which obviously is very useful to people. But on the other hand, no one said I failed 1,000 times doing this various kind of things. Like retrospectively, when there's no AI or large language model, it's probably the right way to do things. But like, we have a database of failure, It will be so useful moving forward, isn't it? It's just a random thought.
Yeah, I mean, like a journal called Honest Insights or something like that.
The book of failure. That's right. So now I'm a clinician, and I need to see like, okay, so 3D printing versus MEW. What can MEW do that normal 3D printing cannot do from a solution perspective?
Yeah, sure. So, and I can, sort of give some, like all the different examples that are out there
Hmm.
have all followed the similar principle where they look at the anatomical structure of the tissue you're trying to replace, and then you try and make something that approximates that structure. And when you're making things from much smaller unit sizes, you can actually start mimicking and building up
Right.
complexities. And so there are just it's several examples of that. So because we're printing with much finer objects, we're able to then produce something that looks a little bit more like us. If I think about implants that go into the body at the moment, they tend to be blocky, chunky materials that look nothing like us.
Yeah.
And so, if we think about a lot of the ECM in the body and the different striations and layers that exist throughout, that we can now start trying to build such tissues. And these are the approaches that have generally had really good outcomes with the research in melt electrowriting.
So what are some of the examples that you could do? What body parts would you work on first?
Sure. I mean, to begin with, thin scaffolds are great, right?
Yeah.
The technology doesn't make large volume materials. Yeah, you can, but it takes a bit of time and there's cost associated with that. So, skin is I think, a great example.
Hmm.
I gave a talk at a conference about 2017, and
Hmm.
someone from L'Oreal was there
Yeah.
and was really interested in maybe we can make a bilayered product that has a membrane where the basement membrane typically is, and
Hmm.
then have a scaffold on the other side made from melt electrowriting that the the dermis would be. Yeah, this worked in the fact that we have a really well formed epidermis where the cells start looking like they normally do in natural tissue, and that's just because the fibroblasts that are adjacent to them but not in direct contact are able to excrete all the factors that allow the
Hmm.
keratinocytes within the epidermis to thrive.
Yeah.
But yeah, I've shown these sections of skin, artificial skin to researchers, and they initially look at it and think, "Oh, that's natural skin," and then they go, "No, wait a sec, hold on," and you see that double take. And working with L'Oreal has been great on this because they challenge us to produce things at like a really high throughput, and this also helped a lot in the research as well, and like trying to do that translation
Hmm.
now, not from not into the clinic, but translation into an in vitro product that can
Industry.
be
Yeah.
widely used, right?
Yeah.
Yeah.
For them probably toxicity analysis for their new cosmetic products, I'm assuming, or some other things. Now, you started with cornea. How is that field evolving? Is this MEW is applicable to that as
um
well?
not really. I mean, I'd love to make that connection,
Yeah.
but I feel that I don't want to put a square peg in a round hole,
Right.
right? And so it's probably been a good 25 years since I worked on the cornea. So it
Hmm.
would mean for me to personally really catch up a lot on this. And I think since I went to Molly Shoykat's lab, my tissue of interest is like the spinal cord or the
Okay.
nervous system. So
And so how about spinal cord? Is this working?
well, for within spinal cord, again, you have the issue. Well, can MEW really help? And so, quite recently, we had a postdoc here from Germany, and we asked this question about getting two types of cells mixing that normally don't. So, in spinal cord injury, Schwann cells are normally taken from the peripheral nerve and transplanted, but it
Hmm.
doesn't really work because Schwann cells and astrocytes don't like each other. They don't mix. They form these boundaries. So what we've done here is to like put down really discrete single fibers and actually put Schwann cells and astrocytes and get them to
Mm,
intermingle. And so it's quite phenomenal. I mean, this is
yeah.
unpublished data, but it's going to be great to show that
Yeah.
you can induce cells that normally just don't like each other to mix and intermingle. And then this also now allows things like neurons to grow over in through the other side. So it's an interesting area of like topography and in vitro research and how that could inform in vivo. But that's kind of where things are at the moment. Again, it's a little bit hard to think specifically about spinal cord injury and applying MEW to it. You know, remember when I said I had that breakthrough of melt electrowriting?
Yeah.
This was a time when I was doing pretty much 80% of my time was on spinal cord injury and working
Mm,
on that tissue.
yeah.
And then when MEW came along, it's like, well, okay, now this is taking a life of its own. And so I think that my focus on the nervous system had to sort of be set aside a little bit as this technology that could be used in so many more tissues
Yeah.
gains traction and then gets used in other
Yeah. I
just as
mean,
important
it's
injuries and
become,
diseases.
yeah, it became a momentum. It's become movement, is what I'm trying to say. The MEW is a movement in a way.
Yeah, I think the past 5 years have been quite dramatic, actually,
Ah,
and this is thanks to funding from the European Union and also China doing a lot of investment in that,
yeah.
and if you invest in any area, you get a lot of outcome and
It's
results.
policy driven
Yeah,
sometimes.
yeah.
Yeah, absolutely.
Um, but I tell you what, it's a delight to wake up and see there's a new paper and go and check it out and see what cool things people have done and used it for and
Yeah,
in other tissues. Yeah.
I'm not a scientist, right? But I have a platform called Pitch 3D where we evaluate startups and stuff, and people bring us all kinds of applications. They're more of a solution focused, and a lot of them use various 3D printing technique. I've seen companies in our last brief, less than 10-year span, people want to regenerate cornea, people want to regenerate neurons. I mean, they're all there, but listening to you, it seems like this kind of dreamlike goal has been there decades ago. So it's really actually a short period of time if you think about it, how we start to tackle those problems. I'm just kind of, you know, it's, like, okay, you already worked on cornea, what, 30 years ago? Almost 20 years ago?
People have been doing this for,
They're still
working on
doing
cornea
it.
for centuries and are still doing
Yes.
it. And
Yeah.
for, that's one of the most sobering things, like, so like with spinal cord injury, like since
Yes.
I was working in about the year 2000, there have been some improvements, but not much, like 25
Yes.
years.
Yeah. And it's not
Yeah.
just bioprinting or bioassembly. I've seen like other startups pitching to us just from a biotech, like other biotech techniques to trying to regenerate spinal cord injury or peripheral nerve injury. It seems like there is some new solutions, but it's not the holy grail I can make you stand up again kind of thing.
Yeah. Yeah. And
Yeah.
so, yeah, I think it's, yeah, the thing is, a lot of the motivation for what we're doing in science is spot on and it's accurate. What we lack are the tools to be able to deliver on the thing that we're trying to solve. And
Yeah.
if I think of MEW as like one tool on top of all these other different tools,
Yes.
it's probably not going to be a single technology that's the magic bullet. It's going to be a combination of those, and then things
Yeah.
get complex because, well, what combinations and all of these different permutations, and suddenly that experimental tree gets significant.
Absolutely.
So,
Well,
yeah.
now we're onto the topic of tools. Um, let's talk about the open source hardware
Hmm.
movement with MEW Run.
Yeah, the Muron. Yeah, we call it the Muron.
Yeah,
So
Muron.
the Muron, yeah. So MEW, melt electrowriting, is also called Mu. A lot of people
Hmm. Yeah.
who work with it, and so if you think about the cost of getting involved in this technology, it's significant
Hmm.
because the customer base isn't huge, right? So we borrowed an open source printer that serves the hobby community. and they're about $700, and they're really robust. There's like it's a high performing 3D printer, and there's a whole community around that, and it's about hobbyists, and the costs are so low. So what, maybe I just sort of go back a little bit. Like, if what we're trying to do is we're trying to use a processing technology to come up with some new design of a scaffold that can then be used to solve a problem. So one of the things I think is interesting is that if you get that processing technology and you strip it down to the absolute basics, you change a fundament, and in this case, it could be cost, it could be size, it could be switching from syringe over to filament, it could be a range of different things, and then build it back up. You end up with a piece of equipment where suddenly you're asking fundamentally different questions. Okay. So in this instance, we now have a $7 MEW printer. The commercial ones are, I don't know, 50,000, 100,000.
Wait, did you say $7?
700, sorry.
Oh,
700. Did I
700.
say?
Okay.
Did I say $7? Yeah,
Maybe
700.
$7 in Uganda, but maybe not.
Yeah.
Actually, not
You
in
maybe have to
Uganda
get
either.
below $100 in the future.
Yeah.
But so
Reduce the
you get,
cost. Yeah,
you reduce
definitely.
the cost, and then suddenly things change because you don't care so much if you destroy it. All right, you could put it in an extreme environment, and if it breaks, you can just fix it with small dollar components. There's no warranty. If something comes into the lab, then it's worth $100,000. The last thing you want to be doing is opening it up, voiding the warranty, and starting to
Right.
modify it.
Absolutely. I have seen
Um,
actually real life example of that.
yeah, it comes to
Yeah.
it comes to an
People
issue
don't
that
even
if
want to use it because not just tinker, but not even want to use it.
yeah, it does come to the issue, like, if everyone just buys pre-built systems, then everyone starts doing the same kind of research. All right, I see that a little bit with extrusion-based bioprinting, and how can you iterate and how can you invent new things using a system that is low cost, fully modifiable, and it's been tremendous. We have something like 20 in the lab at the moment, and it's a printer that just does one thing and does one thing really well. It doesn't try to, like a bioprinter, tries to print all these body parts. Like, now we can say, well, let's just have this Muron. The
I
only thing
see.
it's going to do is print a nerve guide. That's all it's going to
Dedicated
do.
to body
And
part.
yeah,
Yeah.
yeah, or a plastic, a certain plastic. This is the we don't we and we can build it in a week, and then it's running. So it does change a lot. Also, if you're looking at the world dynamics
Hmm.
with melt electrowriting, Europe, Australia, China dominate the number of publications, number of labs,
I didn't know
etc.
that.
Oh yeah, and now I'm on Team USA. It's like, okay, how do we how do we enter this and enter
Yeah.
this market? And the way is, like, do it disruptively, and
Hmm.
that's where the Muron is able to disrupt the the whole process of acquiring this technology. Together with Ohio State University, we do have a build your own MEW printer workshop. It's held every summer, last summer, this summer. It's probably a bit late because it's all the parts are being ordered in. But yeah, it's really cool. We have 8 people.
Is it only for University of Oregon students?
No, it was open for anyone in the world. I think we had 8 applicants this year, so that'll be great. 8 people will come in. It's a good number, actually. 8 people come in, build their own Muron, take it home with them, and then they have a little bit of skill in how to operate, run it, fix it, etc. And
Okay.
we just keep doing this every year.
Well, let me
Um,
know the link. Maybe
yeah,
I'll join you next year, but at least give you a shout out next year for people to sign up for your workshop.
yeah. So what it does, it just fundamentally changes the landscape
Yeah.
of how you use this technology, and then all the different variants and personalization. So I said
Yeah.
we have 20 Murons, but probably only about 4 or 5 are the same as each other, and the others are like unique systems that we publish, and then we can also have them open source so anyone else can reproduce what we're doing.
Yeah, it seems like you're stimulating creativity, which is something that's very difficult to harvest, to be honest. You cannot force people to be creative. So I think open source in general is kind of stimulating people's creativity. I mean, now we're in this era of AI war. The open source versus proprietary software is clearly demonstrating the very polar opposite effect of what's happening, and it's interesting as well. I'm observing it closely. I mean, obviously, 3D printing industry is not as well funded as AI industry, and this is still, within our niche, this is very interesting to observe the open source growth, the metrics that over time, since you're fairly new, you're like, what, 20 years old or something, versus a much older process, the extrusion-based 3D printing, and a bunch of other processes. It would be interesting to see the metrics of growth over time. And since I have a lot of free time, I'm gonna
I
try
could
to
show
track
you.
it.
We're actually about to publish a review, so we've got some of
Okay.
those numbers as well. And actually, just on AI as well,
Yeah.
the because we're pulling from the nozzle, we have some excellent visual access to really important information. So we really are leaning into having AI based fabrication,
Yeah.
and this also is cheap once you know how to do things.
Yes.
Like it should also be able to go into the Muron and maybe be able just to produce things without you really knowing how it does that, right? So at the moment, there's a need for coding, a certain technique. Like you don't just need an MEW printer; you need an MEW user in a way,
Right.
because there's a bit of an
Yeah.
art to work with it, and so it'd be great to take that art away, and then just
Yes.
be able to have it as a system anyone can use. That's
Yeah.
you
To
know,
be more consistent in terms of generating the
yeah,
results. Well, in terms of that, just, we're not trying to dig too deep in the technical aspect of things. What do you think are some of the, I mean, you already mentioned some of the advantages, obviously, from Mio, but what about some of the limitations and things that you could improve upon from both the process side to the material side?
sure. So MEW does, it makes things that are highly porous compared to other scaffolds, but it doesn't make things that are large. So they tend to be limited to several centimeters in width through to the height. Maybe probably less than a centimeter under most circumstances.
1 centimeter, okay.
Yeah, so it's definitely small, much smaller than what FDM can produce because the throughput of the polymer out is a lot less. But at the same time, it's more than what, say, two-photon polymerization, another high-resolution technology, can do. So, the ideal technology is where you have like high resolution and significant volume to it,
Yes.
right? If you think about a
Yes.
lung, right, that would be fantastic to produce. That's one of the hardest things to achieve.
All right. Okay, so let's see. You wrote an article about taming the jet. It's one of the highest referenced. It's very technical as well. You want to just share a little bit about that article?
Well, what we tried to do, I mean, that's actually part two. So we created a series of papers, and
Okay.
in 2015 there was another paper which has summarized all of the melt electrospinning work done in the history, right, from the turn of the 20th century.
Okay.
Then,
I need to find that one.
and then 5 years later, we wrote Taming the Jet. Yeah, which was just a follow on. We don't have to talk about all the same old stuff again. That really reflected the fact that we were able to master and control the jet. If you're looking back in the early days in 2013 or so, we were having, a lot of defects in there and we weren't sure exactly why. And I think then the community was able to work out, oh, this is why this is happening, and we solved it. So that's where the taming the jet came. But you don't just want to make beautiful structures; you want to be able to apply them to and put them to work.
Hmm.
Um, and so I think we're actually just finishing that third part in the review,
Yeah.
and this is a little bit more like from taming the jet to tailored structures for tissue engineering. And that's definitely what's happened in the past 5 years. A lot more applications have been tested out, and also a lot of different plastics have been tested out there. two major focuses of research. And then I think also a big trend has been the imaging of the jet and actually how that would tie up to AI
Hmm.
and sort of camera vision and computer vision within that. And actually the final thing that I think is going to be transformative is a really good user interface, right? The
Yes.
better the user interface, the more people you can have working with a system.
Foolproof, like me. I'm the
Yeah,
fool. If I
and
can
again
use
with
it, you definitely passed.
yeah, and I'd like to have someone who has no experience, like, say like a biologist, right, who knows that want to make something, not sure exactly how to take all that jargon out, and that's where I think a good user interface, probably generated using a large language model, right? This is improving a lot together with AI based fabrication to really enable potentially to even upload scans of tissues that you want recreated, and then it will try and approximate that for you, right? So
Wow, that would be
that would
amazing.
be cool. Yeah.
You just put
So
some ideas in my head. Uh, I mean, crazy ideas in my head. But yes, I can see that. I can see that. But then I know it's going to take probably decades to actually get there. It's possible to take decades, or maybe shorter. Who knows? Um, and then the other, so I've been going through your publications. I have to say, there's no way we can talk about all the publications that you have published in this 60-minute conversation, which is approaching 2/3 now. But I just picked up a couple because they're the top cited one on your Google Scholar. And the other one I think is very interesting. And also I heard you talk about this in the past, is do not equate bioprinting with biofabrication. And I have to say, I have committed crimes by doing this quite regularly. So I apologize for that right now, just right now. And I will definitely try my best not to equate and be more precise. But I also think at the same time, it would be very helpful if you can just make sure, clarify the boundary of these words and how do you envision biofabrication really is going to be from now on.
yeah, I probably have a different um, definition compared to most in the community. My feeling is that biofabrication is the automation of tissue engineering, or the automation um, of being able to produce tissues, because bioprinting is one aspect, and I've spent so many years also manually pipetting, right? And now a robot, and now a robot's doing it. Well, it was for me, your mind wanders, and it's like, oh, did I just pipette this in here or not? And then you have to throw everything
Right, you
out and
can't even
start
see, you
again.
can't even see. Yeah,
Yeah,
exactly.
yeah. Um, but I think bioprinting is a tool, right? And I think we need to kind of gather the tools. We need to gather our abilities to better automate and better produce things. And in the early days, extrusion based bioprinting was considered, like, a lot of people just used it for biofabrication. And for me, I thought that was a very risky thing, because if extrusion based bioprinting doesn't really deliver on the goods, then the entire field of biofabrication becomes under assault. And for me, the automated production of tissues is very logical. I don't think too many people would think that's not the future
Yeah.
of production, right? So for me, that's biofabrication, and extrusion based bioprinting is one. There's also like volumetric bioprinting. There's many
Yes.
different forms of bioprinting, and I think from a simplicity's sake, everyone just focus on extrusion based bioprinting, which I think's probably had, I don't know, it's probably had billions of dollars of R&D spent on it, and there's
Yeah.
a real question: has it delivered on that? Since 2010, this became a thing, and you've had a lot of money put onto it. Have we done all of those things that we said we would or promised? I'm not sure, but I think the solution is a lot more thoughtful way in how we're using automation when we're assembling things. And
So yeah, I also learned, I mean, by just reading briefly some of these articles, bioassembly is also part of the biofabrication. Is bioreactor the same thing as bioassembly, or these are different? Or because I've
I would
definitely
say,
seen bioreactors a lot of different places now in commercial space.
yeah, I mean, I think it's part of the automation process, right? because you need to mature a tissue, and also you need to be changing things. I don't think you just set a bioreactor to the same conditions for a week, go away and then come back. It must be constantly changing with time. And, maybe in the future, whenever we print a heart,
Hmm.
all right, it's not going to be, oh, suddenly it's working. We're going to know exactly what we're doing by then. And it will be like hundreds of variables switching on and off in synchronization, aided by the natural repair of the body, but not, governed by it.
Hmm.
So I think it's going to be an incredibly complex task. And that maybe this is where AI is going to be helpful, being able to help us pass out, give us our best guesses and to develop protocols that enable us to understand really complex production approaches. And when,
Yeah.
when it's hard for your mind to get around like a 5-dimension graph, imagine how hard if there's 100 variables in that, like 100
Yeah.
dimension.
Well, that does sounds like something you need AI for. I mean, this is biology is actually probably one of the hardest problems in for humanity is to really understand our own biology. So people obviously would kind of like look at AI nowadays seems to promise someone who's smarter than us who can figure this
Mhm.
out for us or something
Yeah.
like that. But anyways, I digress. But it is something that I think it just like you said, you want many powerful tools working together to achieve a great result for biofabrication. So I think AI could be playing a pretty important role in that. So what do you think with MEW? What do you think in the next 3, 5, 10 years? So in other words, short, mid to long term, that you have vision in terms of either research or just clinical application, either direction. What do you think the trajectory is?
Well, there's going to be two general trajectories. One will be implantables, and I think they may be close to human implantation in Australia. The
Okay.
the plastics that are used tend to be medical grade polymers, and also polymers working like melt processing is established for decades in safely making biomedical devices. So that part's not strange. There's already FDM based biomaterials out there. So now the only thing we're changing is a high voltage. So we're not changing too much using this. So
Hmm.
I definitely by 2030 there will be MEW implants in people for sure,
Okay.
because of the safety of doing that is there.
Is this going to
Yeah.
be skiing? Because you mentioned skiing is probably the easiest to go to.
I honestly don't know. I mean, it could be skin. It could be. I think the thing is, everyone has their own specialist and their disease or injury they're trying to treat, and MEW is now coming up on the radar. So it it's just really hard to fully gauge.
Hmm.
If we look at the in vitro work that's being done, that's really compelling. And so maybe then that ties together with the in vivo results. Some great products that come to mind is in Perth, in my hometown. There's a lab that is making heart valves,
Hmm.
and these heart valves are are, are better than existing
Yeah.
because they open up really well. So the patency is like really, really good. There's some great work actually out of China where you have, I think these are cardiomyocytes as well. What I liked about the study where you actually had two fiber plates held together with this tiny strand of fibers
Hmm.
is that the cells adhered to one part of the scaffold and then moved off it and then used another part of the scaffold for its mature period. And so that's quite interesting, really seeing this transition of cells behaving this way at the start of their culture and then really changing in how they behave later on. So there's that. Hernia meshes, yeah, come to mind as being something that could be really useful. Prolapse meshes, perhaps.
Well, you also had a startup. You're a co-founder of a startup,
Yeah,
correct?
yeah,
And
yeah,
that's also working on some of end applications with MEW, and it's called Vivotex.
yeah.
You want to tell us what Vivotex is doing nowadays?
Sure. And so Vivotex is like the accessibility thing. So on one side we have the Muron open source where
Yeah.
people can get access and research. What Vivotex does is they just sell you really good scaffolds, and they
Hmm.
sell that to you in a format that you can just start using in your own process. So you don't need to have a printer, you don't need to have a user, you don't need to spend 6, 12 months getting this up and going. You can just buy scaffolds and start using them the next week. So, what we've done is industrialize the process so that the scaffold itself can just be a commodity that you can buy and use. And I think it's a tremendous opportunity, especially for companies as well that, have time pressures. They already have existing workflows. And we're really trying to ensure that what we're making fits at Vivotex fits into those workflows. And so you can really bypass a lot of time and a lot of money in trying to acquire your own system and learning knowledge. Because I don't think the printers are there yet, right? Probably in another 5 years, you can get a printer and it will just work really intuitively and automatically, but it's not there.
Yes, actually, there is no commercially you can purchase MEW printer, is there? It's only
No,
open source.
no, there you can for sure. There's about 6 companies, all are based out of Europe and China, who actually
Okay.
have MEW printers or an MEW head on their
Hmm.
bioprinter.
Okay, that's good to know.
Yeah, yeah. So you can get commercial systems, but I do think that the price is really high because the customer base isn't big.
Very small, yes.
All right. And it's just the scale of economics and where things are at. And
And
I just
also
also have,
MEW users are very expensive to acquire as well.
yeah,
There's
sure. I
not
mean, you're
many of
paying a
them.
salary. Yeah,
Yeah.
yeah. There's a good growing number of them, just through a lot of the education that's happened. But yeah, they're expensive systems, and it can just be done more efficiently in other ways. And MEW is not like bioprinting, where you can actually have a product on the shelf for years, and it doesn't change. Whereas with bioprinting, you've got your gel there, and you want to put cells in, and so you need that bioprinter there to do your research. But here you can have an off the shelf product that can sit there for a long time, is easily sterilized and properly packaged. So that's where Vivotex is focused on. It's just the accessibility through making the products a commodity.
So after all this, do you know everybody in MEW community?
Yeah, I think so. I think so.
How do you
Um,
monitor this community if it's growing? Like,
well,
uh
it was easy.
do you have a convention every year?
In in February, I took part in the I-Corps program in the US,
Okay.
and so that's where we had to do 100 interviews. And so, yeah, we reached out and we learnt new people working in MEW and was able to talk to them.
Yeah.
And so
A
yeah,
100 interview, that must be a really fascinating experience.
it's great. It's actually really, really good. And it's a 6 week period. So, and that's really about customer surveys and trying to understand the landscape. And this
Mhm.
was actually with relation to the Muron, like the open source printer. Like, how can
Yeah.
we make it? How can we make it better? How can we make it more accessible? Is there ways we can better train people or have experiences? So
Are you
it was a,
allowed to share the inside of that?
yeah. I mean, the inside is actually one of the things that we really learn is that in 3D printing, you have someone called makers who like to make stuff, but there are two clear, distinct types. There is one called the builder maker. And what they want to do is actually assemble and put together that printer, test it out, and then they go, okay, job's done. Where's the next thing to build? And
Mm.
then you have a user maker that doesn't care how the printer works. They just want to make stuff with it.
Mm.
Okay. And people are generally in those two camps where they either really enjoy building things and getting it to work and then handing it off, or, just printing. And so people who just want to print, you can get a bamboo printer and you can make some great things at home, but, you're limited by the printer that is there. Whereas, and the builder makers are really less common than user makers. And it's also very rare to have someone who's both who likes to build the printer and then actually use it for printing. So, yeah.
So, for people like me who are just a clinician, limited engineering background, want to get into biofabrication, what are your some advice? I know this is a very general question, but
I think read. I think you have to be mindful of any new technology of hype, and you just want to be able to filter through the hype a little bit, understand what's been done before you, and also the people that are before you. They're super smart, intelligent people, and they weren't able to work it out. So you should, be a little bit cautious, as you're going forward. That that you're making the right decisions. Um, so my recommendation is to really start off with a, a bunch of reading, and then maybe learn about some of the different technologies and the strengths and weaknesses of those. And I think what you can do is, ideally have two technologies which have weaknesses that you bring them together, and then they don't have the weaknesses anymore. It's like 1+1=3. And trying to find the combination of technologies that really do enable you to do what you.
so for people who want to, who are working on Muron, who's becoming part of the community, what is the first project you want them to try on?
The first thing actually I'd like them to do is to print with medical grade polymers. Right,
Okay.
like there's a lot of things you can print with, but if you start printing with medical grade polymers, the outputs are better. Like it just prints so much nicer, as well as being the kind of material that you would actually want to use later on.
Mm-hmm.
So in our lab, we just don't have any Sigma Aldridge polymers and that we really try and work with medical. So medical grade PCL, send me a message. I'll send you a Falcon tube of it. I've done that to many people saying, look, just use
Wow.
this polymer, and then they have like a multiple step change improvements over that. And it's a little bit because the purity of the PCL that's used in the medical grade is better, so it just processes better.
Mm-hmm.
And my biggest recommendation to anyone starting is just work with high quality polymers. Maybe a bit expensive if you finish the Falcon tube that I give you, but it's ultimately worth it in
That's
time
amazing
saved.
offer. I gotta put that, make sure I put that in show notes. So we are reaching the end, but I feel like it's just the beginning of many conversations in the future, because I can see this is a growing community, evolving technology. I can see that every year something new is going to happen. So hopefully I get to invite you back. Now, at the end, we're at the end. So can you provide some possibility for people to perhaps contact your lab, how to get that free filament that you're talking about, and other
Yeah.
resources to learn?
Yeah, so it's easy. I mean, it's easy to find me if you Google my name, or if you even just Melt Electrowriting or MEW. I'm based at the University of Oregon, and our lab does, a lot of internal work, but we also do a lot of work where we're just helping others. And so we make sure we carve out time to assist others in the research that they want.
Awesome. I'll definitely put the links that we have talked about in our show notes. Professor, thank you so much for talking with us today. I hope this is going to be the first of many conversations in the future.
Great. Thank you. It's been awesome to speak with you.
This podcast is for educational and informational purposes only. The views expressed do not constitute medical or financial advice. The technologies and procedures discussed may not be commercially available or suitable for every case. Always consult with a licensed professional.